few people get their food. I just want to start with a few slides about the COAST program, which is the Council on Ocean Affairs, Science, and Technology. This is an organization that gave us a grant to bring Rafael here today. And so we just wanted to show you a little bit about what they do. COAST is the umbrella organization for marine, coastal, and coastal watershed-related activities within the CSU. And they promote research and education to advance our knowledge of marine and coastal resources and the processes that affect them. The scope of COAST covers everything from the open and coastal ocean to coastal zones and coastal watersheds. And not only are they very involved with research and outreach, but something that's important for all of you to know for sure is that they also have great funding opportunities. They sponsored the award to bring Rafael here. They also have student travel awards up to $1,000, and they're available for travel from January to June of 2018. So you can check their website to apply for that ASAP. There's also a summer student internship program with a $4,000 stipend where you can work with professional scientists in California. They'll be announcing that in January. And then there's a faculty grant development program, up to $15,000 seed grants to support activities to maximize success in obtaining other external funding. And they'll be announcing that later this month with proposals due in February of 2018. So we're very happy to have Rafael Cuevas-Uribe here today from Humboldt State University. Rafael graduated with a BS in biology from the Universidad de Guadalajara in Mexico. His thesis was on hormonal sex reversal in tilapia. He got his master's in aquaculture and aquatic science from Kentucky State University, studying genetic sex control in the black crappie. And his PhD in wildlife and fisheries from Louisiana State University on sperm cryopreservation in aquatic species. He did a seminar here at Moss Landing about the use of cryopreservation in aquaculture last year. He did a postdoc at Kentucky State on paddlefish culture and using reclaimed water for aquaculture, and he's on his third year at Humboldt State University where he teaches courses on aquaculture, advanced aquaculture, mariculture, fish diseases, and ichthyology. His research interests include reproductive biology, conservation of genetic resources through cryopreservation, and integrated multi-trophic aquaculture systems. Rafael.
Thank you. So today I'm going to be talking about some of the research that we have been doing in aquaponics at Humboldt State University. When we define aquaculture, we always think about aquatic organisms. So today I'm going to be talking that it's not just aquatic organisms. We also produce terrestrial plants. For example, aquaculture raising 600 aquatic species, and we know a lot of them, and none of them are listed as terrestrial plants. And this is one of the purposes of aquaponics that we are going to be learning today. There is a classification depending on the production methods that we raise these aquatic species, and there is three big categories that is going to depend on how do we control the temperature, dissolve oxygen, and how do we manage the waste. So these methods are divided into open system, semi-closed system, and closed systems. And there is a fourth method that combines some of the benefits and limitations from the other ones. So these are known as the hybrid systems. Basically, we are talking about partition aquaculture system and the integrated multi-trophic aquaculture, which I'm going to be talking today. So what is an integrated multi-trophic aquaculture? Well, it's the use of the byproducts. This could be leftover feed. It could be feces, waste from one species, and it's recycled to become the input into another crop. We have basically two types of integrated multi-trophic aquaculture. One is going to be the marine integrated multi-trophic aquaculture. A good example of this, and within the marine integrated multi-trophic aquaculture, this is divided also into two parts. One is the open water marine integrated multi-trophic aquaculture. A good example is the lead country on this is Canada, where they have salmonid species, that's the fed species, and they use other byproducts to produce other crops. In this case, shellfish, seaweed, and sea urchins, lobsters. Now, why here in California, why we are not doing this type of system? This is the future. What happened? What is going on? And what happened is we have all these permits that if a farmer wants to get into aquaculture, he needs to go into this line and pay, I don't know how much money, but at the middle, he's going to run out of money. In a recent book, they say that there is 1,300 laws that apply here in California about aquaculture. So it's really difficult for a farmer to have a system like this, and especially in the open ocean. Who lives in the open ocean? Who can afford to have this nice house? They don't want to see some cages growing fish. They pay a lot of money for this nice house, and that's also one of the reasons, and the political influence that these people have. So the other system is going to be a land-based marine integrated multi-trophic aquaculture. So this is what we have to start focusing here in California. If we cannot do offshore or open ocean, let's focus on something that we can do inland. So basically what we have here, again, we have a fed species, and we have a filtration system where we have some other species utilizing the byproducts from these fed species. One of these examples, such as this one, is in Florida. So when I got the invitation to come here and do this seminar, I really wanted to talk about the system that we have at the Marine Lab. It's a pilot system where we try to have the same concept. In this case, the results are not that great, and I'm just going to briefly mention what happened with this system. So we have in this tank, we decided to have Sebastis, rockfish, and this was leftovers of fish from a project. The idea is to use all these waste, we call it nutrients, and in the second, before going into that, we have to feed something to rockfish. So it's difficult to train on a small rockfish to eat pellets. The first thing that we tried was autoheme or autohyme. But once that pellet fell into the bottom, because this is a sinking pellet, they don't really chase or eat from the bottom. So we tried another type of feed. This is the golden pearl. This is a neutrally buoyant pellet that is going to stay longer, so in that way the rockfish could eat. Unfortunately, the taste was not something that they really liked, but in the same company, they have these marine pellets. That's something better. Again, they just eat. If we use floating pellets, they don't eat from the surface. The only thing that they eat is whenever the pellet is slowly sinking. So the idea is to use all these leftovers and have a filtration system. In this case, we use Kumamoto oysters that are going to be eating all those suspended particles. the water is coming into a reservoir and into a filter. These filters, they are known as endurance bead filters. They are filled of this plastic media. This plastic media flows. It's going to allow two things. One, it's going to have enough surface area for the nitrifying bacteria to colonize, and the other one is going to collect the solids. So it does biofiltration and solids removal in one filter. Nowadays, they are not that expensive, and the one that we use is rated to have as many as 1.5 kilograms of feed. After flowing there, we have a Humboldt where last year I got some gracilaria from Mike's lab, and we were trying to culture this. So what happened is this. After 4 months of running the system, the rockfish just grew from 1 gram to 10 grams. And that's not good for an aquaculture species. You want a species that is going to get a market size as soon as possible. So we decided that rockfish is not the best species to have in a system like this. And also our gracilaria, instead of having more gracilaria, the biomass was reduced. It could be, one thing is the temperature. We have enough nitrates and phosphates in our system, so we were not sure what was going on. Why do we have this reduced on the growth of gracilaria? So the next thing that we decided to do is, let's do other species. So by reading the literature, we found out that NOAA has a research station in Washington where they do sablefish. So we drove to Washington, and they donated some sablefish for this project. Unfortunately, halfway down, one of the tubings in the oxygen line broke, and we have like 50% mortality, but half of them make it. We decided also to change the seaweed. We did Pacific dulls. And again, the research, I mean, the sablefish was growing, but once we reached the summer, which the temperatures are 16 to 17 degrees Celsius, that's definitely too warm for the sablefish. So we have also some mortalities, and the same, the Pacific dulls was not really growing. So a couple of weeks ago, we just decided to move this system, instead of being indoors, to have it outside. So now we have the system outside, and again, what we want to see is what kind of nutrients are we lacking in our system. So we are conducting some experiments and see if there is any micromineral that we are lacking, or what is the reason why our seaweed is not growing. So this is something that I wanted to make a whole presentation for this seminar, but like I say, I don't have really good results. So I'm just going to be talking about the other form of the integrated multi-trophic aquaculture, which is the freshwater systems. These freshwater systems sometimes are known as integrated fish farming, which includes aquaponics. Also, some people use the manure from the livestock as a fertilizer in fish ponds, or also the sewage-fed aquaculture or polyculture. So all these are different types of the freshwater integrated multi-trophic aquaculture system. And today I'm going to be focusing on the aquaponics part. So what is aquaponics? Well, that's the integration and balance of a recirculating aquaculture system and hydroponics. And a lot of people jump and say, oh, hydroponics, great idea. But is aquaponics. A lot of us fell in love whenever you do a Google search. You will find all this beautiful image, and you're like, wow, aquaponics, it's just beautiful. But in reality, it's like a marriage. There is not such a perfect marriage. You know, people tell you, oh, it's a perfect marriage between plants and fish. But at the end, there is always something in the middle, and this is going to be the bacteria. You know? So you have to have this bacteria in order to have a full system running. So you also are culturing bacteria in your system, besides the plants and the fish. Now, where does this concept of aquaponics come from? Well, we want to use the byproducts from the fish. In this case, if we feed them 1 kilogram of feed, the fish is going to be consuming oxygen, it's going to be producing CO2, and it's going to be producing ammonia, and also some solids. So the idea is to use the ammonia that is being produced, the CO2, and the solids to produce another crop. Normally, a fish, 1 kilogram of feed, or the fish feed is going to have 45% of carbon, 6% of nitrogen, and 1.2% of phosphorus. How much of this the fish is going to be able to uptake and retain? The answer is not that much. Just 13% of the carbon, 30 to 40% of the nitrogen and phosphorus. This means that most of these nutrients are going to be excreted. In the case of nitrogen, it's going to be in the form of ammonia. So we want to use all this to produce another crop, in this case, plants. So the nitrogen cycle, we have a component that is going to be removing the solids. We have our biofilter that is going to be able to oxidize that ammonia. Traditionally, nitrosomonas bacteria are called the ammonia oxidizing bacteria that oxidize ammonia into nitrites. And then we have a secondary type of bacteria, traditionally known as nitrobacters, that are going to oxidize that nitrates into nitrites. And then the plants, that they are going to be consuming that NO3, that's the preference nitrogen source for the plants. And then return. So it's a fully recirculation system. More or less, they say that you can grow 1 square meter of plants if you use about 60 to 100 grams of fish feed. That's the ratio that they recommend. Where does the aquaponics idea come in Humboldt? Well, what happened is they used to have a pulp mill, but it got decommissioned. And the Humboldt Bay Harbor District decided to have a big plan on reusing this land. And they came out with the National Marine Research and Innovation Park project. Part of this project was to have an aquaponics system. So before start this big plan, they bought an aquaponics system from Nelson and Pate. This is a picture that they sell you. So a beautiful system. Nelson and Pate is a company that is going to just sell you systems. So they bought the system about 5 years ago. They assembled the system, and they realized that it's not that easy to run. It has a lot of different tricks. So after a year, they just gave up, and they decided to take it apart. So when I arrived 3 years ago at Humboldt State University, I found the system like this. And they say, well, can you use the system? And I say, great, yes, that's what I want. I was teaching an aquaculture class back then. So the project was, for the lab part, was for the students to assemble the system. And they assembled the system, and we were raising sturgeons. So I'm going to be talking about some of the research that we have been doing in this aquaponics system that is located at Samoa in Humboldt County. The system is just a copy, a miniature copy of the system that is used at the University of the Virgin Islands. This system, it has several components that I'm going to be talking. So we have the fish tank, solid filtration, a filter, the hydroponic tanks, some pumps, aeration, and a backup system. So this is more or less how does it look. So we have the fish, then we have a clarifier that is removing the settable solids. We have a filter, also known as a mineralization filter. We have the hydroponic tanks, and the water is flowing back into the fish. We decided to use sturgeons. We didn't have any other option. What happened is these systems were designed at the Virgin Island. It's a tropical weather, and they are designed to hold tilapia. But once we requested to Fish and Wildlife to raise tilapia in Humboldt, they decided that it's not feasible to do tilapia. So then we asked, well, what about catfish? They say, no catfish. Well, what about hybrid striped bass? No. So the only options that they gave us was mosquito fish or sturgeon. So we decided to do sturgeon. So yeah, and I mean, we got them really small. Nowadays they are this size. And we feed them sturgeon diet. Now, that's a fish tank. The next component of an aquaponic system is going to be a way that you are going to be removing those big solids. This is done normally with a clarifier tank in the case of the U.S. Virgin Islands. You need to have a 20-minute retention time for those settable solids to sink. So again, the water is flowing into this clarifier tank. It's going to hit this baffle. It's going to have those 20 minutes retention time that the big solids are going to sink. And then you can remove those settable solids. The next step is to have a filter, a mineralization tank that is going to break down all the organic components and make it more available. So it's going to break it into essential inorganic nutrients. This is, again, at the Virgin Island. They use this orchid netting. But there's a lot of work. They have to clean once or twice a week. We found out that these two components were not doing their job. It's just difficult for a clarifier to have those 20 minutes retention time. And at the end, our system was, it didn't work as it was expected. So we decided, why don't we combine this clarifier and this filter and use a bead filter. So that was the first thing that we decided to do. So we changed those clarifiers with a bead filter, and it works perfect. The good thing of the bead filter is that also it's going to have a storage tank that is going to store the sludge or the waste. Now the next component is going to have that hydroponic unit. In the Virgin Islands, they use the raft methods or the deep flow channels, but there is all these different methods. I'm just going to briefly mention those. We have, like I say, the same as the raft systems. We use the media. We use 60% coconut fiber and 40% perlite to grow our plants in a little basket. We have air stones flowing into the rafts. One of the disadvantages of these systems is that if you have a lot of solids coming here, they are going to build up in the roots, and it's not going to allow the plant to absorb the nutrients. But there is other ways, such as the nutrient field techniques, the aquaponics. And I always have this slide here because in Humboldt, they always ask me, can we grow wheat in aquaponics? So I say, yes, probably if you want to grow wheat, then you have to use this kind of Dutch buckets where you have a dripping method. So we were able to produce, just in 60 days, about 216 pounds of lettuce. It was difficult for the students to eat salad. A key important component is to monitor the water quality. You want to make sure that your fish are happy, but also your plants are going to be happy. So oxygen, definitely higher than 5 milligrams per liter. The pH is going to be tricky, as we will see. The nitrification process is going to be, the nitrosomonas and nitrobacters are going to be consuming the bicarbonates from your water. So you need to add a source of carbonates. In a recirculation system, normally we add baking soda. But soda is not something that the plants like, so you have to use something like agricultural lime, calcium carbonate, potassium bicarbonate, to add those carbonates that the bacteria need in order to remove the ammonia and the nitrites. You want to keep all those total ammonium nitrogen less than 1 milligram, the same as the nitrites, and the alkalinity higher than 100. So it's difficult to find a balance. This is what the uptake, the plants, they have a tendency that the more acid the pH, the better available of the nutrients they have. So once you increase the pH, as the fish wants, about 7.5 or 8, then there is going to be some limiting, such as iron. So you have to supplement iron in the system if you have a pH that is going to be about 7.5. So the first experiment that we did this year is compare different varieties of basil. Basil is going to be probably the most profitable plant that you can grow in an aquaponic setting. So we decided to compare all these different types of basil. So we grew them during the summer. And this is the first trial that we did. As we can see, we did what is called a cut and grow back again. So you don't really remove the whole plant. You just remove some of the plant. And we compare the first harvest and second ones. Holly is the best basil that you can grow in our system, following by lime and the sweet basil. Now, we decided to replicate this full experiment and do a second time. So, and we did also 2 harvests. So again, doing this experiment 2 times, Holly was the best one. And look, that lime also did pretty good. But at the end, is what the market is going to value. Sometimes it's not a problem of raising the fish or the plants. It's going to be selling those plants and fish. Because we are a university, the university, it's just hard to get a permit to sell the produce. So most of our produce is going to be donated to food pantries, such as the Open Door Community Garden. So this experiment was done by Brian. And at the end, he was able to process some pesto and fundraise for the Fisheries Club some of this pesto. And he's going to be presenting this research in the upcoming meeting, the Aquaculture Americas, that is going to be next year in February. So that's one of the research. The other one I'm going to be talking next is about another research. And this is to our NSF, the Dulucic project, so Jason Jackson project. What he wanted to evaluate was a fish-free diet versus a commercial diet. Let's look first at the sturgeon production. So this is the captured fisheries of the sturgeons. And look what aquaculture has been done within the last 15 years. I mean, it just grew crazy. And that's why here, sturgeon is really important. You know, Sacramento is the caviar capital of the United States. Now, it doesn't make sense to produce fish and feed them fish meal and fish oil. And why? Because we don't really see an increase on the fish meal. And 63% of the fish meal that is produced is consumed in the aquaculture. But from the fish meal, the byproduct is going to be the fish oil. So about 20 to 25% of that fish meal is going to become fish oil once it's processed. And 81% of that fish oil is going to be consumed by aquaculture. And 70% is just on salmonid species. So if we really want to increase the fish being produced in aquaculture, we have to stay away from fish meal and fish oil because it's not really growing the fish meal or fish oil. And also because the fisheries, this is the fisheries, the wild capture fisheries, is not really supplying any more fish. So we already harvest our limits. So we need to find new ways to grow fish without having to rely on the fisheries. So 2xSeas, a company here out of Sausalito, California, they developed this fish-free diet for trout. And we asked them if they can donate some of this diet to do a project and compare if a sturgeon is going to be able to grow using this fish-free diet developed for trout and compare with a commercial sturgeon excreting diet. Normally, a diet is going to have about 20 to 55% of the fish meal and 12 to 16% of fish oil. So we wanted to see if this fish-free diet is going to be enough for the sturgeons to grow versus just the traditional commercial diet. So we analyzed these two diets, the proteins a little bit higher on the commercial, but then the fat definitely higher on the commercial versus the fish-free diet. And this is going to be some big difference later on, as we will see. We wanted to keep track on the individual growth, so we ended up tagging all the sturgeons in our system. And this is what happened. Unfortunately, the fish-free diet, this is the growth, the individual growth. They were growing really slow versus the commercial diet, which was within the expected growth for the sturgeons. The interesting thing is that the sturgeon was still growing on length, but not on weight. So if we just compare the length, we see them that they're still getting bigger, but the weight was not bigger. Why is that? Well, we send, again, the feed samples to be analyzed for fatty acids profiles, and this is some of the results that came back. So one of them, the fat, as we saw before, is recommended for the sturgeon diet to be 12 to 18%. Our fish-free diet was just 11%. It's not within the recommended rate versus the commercial. The other one, they recommend 2 EPA for 1 DHA, which was really close in our commercial diet, but the fish-free diet, it didn't have that ratio that is recommended. Another thing is if you see all this linolenic acid, definitely they were higher in the fish-free diet, and this could cause peroxidation on the fish and decrease on growth. So that's the experiment. Unfortunately, well, the diet was a fish-free diet, was developed for trout, so that doesn't mean that probably if it's developed for sturgeons, probably they can grow using that diet. So this is an ongoing project that we are doing. So what we want is we're still generating waste in the aquaponics system that is coming out of the filter. So now, is any way we could use this waste? Because it's full of nutrients. So the experiment that we did, or that we are doing right now, well, there is different methods that you can utilize these nutrients. One is the municipal waste, you send it to be treated over there, landfill, mineralization, or what about removing the water out of the waste? Because in reality, just the solid part is less than 2%. Most of them is going to be water. And what around here, what we want is to preserve water. So if we can remove the solid portion, we can send back this water into our aquaponics system. So that's the main driven idea of this project. So what we are doing right now is we are filtering all those solids. We are quantifying how much water are we getting out. And at the end, we are going to send to be analyzed the solid portions and use it as an amendment, as a fertilizer, and grow more plants. So like I said, this is an ongoing project right now, and I'm going to have some results probably in 2 months. So the aquaponics system has been a great system as a teaching tool, but like I say, it's a difficult system. And I'm going to make some recommendations. It has been driving a lot of excitement among the students. Nowadays, we even have an aquaponics system at the hatchery. So the first thing is, can I really make a business out of the aquaponics? And you have to be really careful in how much are you going to be spending. How much are you going to be spending in constructing the greenhouse, the aquaponics system, your operational costs, the price of your crop. So at the end, it's economies of scale. They say the vet area of 75.6 square meters with a basic price of a break-even of $60 per kilogram. And I don't know how much people are going to be willing to spend this much money on basil. So you have to really work on your numbers. So some considerations. Failures abound. You have to be really careful. If somebody offers you assistance, just go and visit the farm and make sure that they are producing what they are really telling you. There is really few commercial models that exist. Regulatory issues are complicated, especially, like I said, the systems are going to be designed for tropical species. There is a lot of people that they just want to sell you the systems, and they sell you the idea that this is a great business, but in reality it's going to be difficult. I always tell to my students that if you jump into the aquaculture business, you adopt a lifestyle. that probably some of your classmates from your high school are going to be driving a Lamborghini, but you decided to work in something that you like. So you decide to live that lifestyle, become a farmer, and you don't really care about the money. So start with something that you can afford. Only invest what you can afford to lose. This is a rule. You don't want to get all the retirement funds from your parents and invest it in aquaponics. And it will always cost more and take longer than you anticipated. Like I say, get an idea, tour different facilities, make sure that those people are producing what they tell you. I want to acknowledge a lot of people help in this project, especially the Cold Seafood, Hog Island, and Taylor Shellfish, that they make some donation to keep the system running. And that's my email if you want to contact me. Thank you.
Does anyone have any questions?
What was the protein source in the non-fish protein diet?
Yeah, I asked the company if they can give us the source. They didn't. I saw a video and they say that they have pistachio meal, soybean meal, corn meal, but I don't know about the percentage. So some of this is proprietary. It's difficult to get the ingredients.
Did your $27 per pound of basil include the profit from fish in your system?
No, that's just growing basil. So normally the fish is like the secondary business. If you do aquaponics, your main business is going to be the plants. And especially if you don't grow tilapia, normally you can get a market size in 6 to 8 months. But in the case of sturgeon, you have to wait 2 years in order to sell this sturgeon.
Would that be improved by looking towards shellfish or something with a faster turnover rate?
Yes, a lot of people, they believe that having probably some crawfish or something in the beds, that you can have another crop, that you can just diversify your farm. Yeah.
Do you have any ideas or any hope to making viable fish food?
Yes, I think that we don't have other options. There is no more fish coming out of the ocean. We already consume a lot of the fish meal and fish oil, so if we really want to produce more fish, we have to go and develop a fish food diet. And it's done already, for tilapia, catfish, and other species. But salmonids is one of the main consumers of fish meal and fish oil. Yes.
What's an input of trace minerals that you have in order to keep your plants alive as well? Does that come from the fish or?
No, there's going to be some trace mineral. One, you need potassium, and that's why we add